Simplest async/await example possible in Python. I've read many examples, blog posts, questions/answers about asyncio, async, await in Python 3.5+, many were complex, the simplest I found was probably this one. Still it uses ensure_future, and for learning purposes about asynchronous programming in Python, I would like to see an even more minimal example, and what are the minimal tools necessary to do a basic async, await example? Question: is it possible to give a simple example showing how async, await works, by using only these two keywords plus code to run the async loop plus other Python code but no other asyncio functions? Example: something like this. But without ensure_future, and still demonstrates how await, async works.
To answer your questions, I will provide 3 different solutions to the same problem. Case 1, just normal Python. Output. Case 2, async/await done wrong. Output. Case 3, async/await done right. The same as case 2, except the sleep function. Output. Case 1 and case 2 give the same 5 seconds, whereas case 3 just 3 seconds. So the async/await done right is faster. The reason for the difference is within the implementation of the sleep function. In case 1 and case 2, they are the same, they sleep without allowing others to use the resources. Whereas in case 3, it allows access to the resources when it is asleep. In case 2, we added async to the normal function. However, the event loop will run it without interruption. Why? Because we didn't say where the loop is allowed to interrupt your function to run another task. In case 3, we told the event loop exactly where to interrupt the function to run another task. Where exactly? Right here. For more on this, read here. Consider reading. A Hitchhiker's Guide to Asynchronous Programming, Asyncio Futures and Coroutines.
Is it possible to give a simple example showing how async, await works, by using only these two keywords plus asyncio.get_event_loop plus run_until_complete plus other Python code but no other asyncio functions? This way it's possible to write code that works. But this way it's impossible to demonstrate why you need asyncio. By the way, why do you need asyncio, not just plain code? The answer is, asyncio allows you to get performance benefits when you parallelize I/O blocking operations, like reading/writing to the network. And to write a useful example, you need to use an async implementation of those operations. Please read this answer for more detailed explanation. Update. Okay. Here's example that uses asyncio.sleep to imitate an I/O blocking operation and asyncio.gather that shows how you can run multiple blocking operations concurrently. Output. Note how both IO_related started then, after only 1 second, both done.
Python 3.7 Plus now has a simpler API, in my opinion, with a simpler wording, easier to remember than ensure_future. You can use create_task, which returns a task object that can be useful later to cancel the task if needed. Basic example 1. Result. Hello 1 started, hello 2 started, hello 1 done, hello 2 done. Basic example 2. If you need to get the return value of these async functions, then gather is useful. The following example is inspired from the documentation. Expected output. PS, even if you use asyncio, and not trio, the tutorial of the latter was helpful for me to grok Python asynchronous programming.
Since everything is nicely explained, then let's run some examples with event loops. Compare synchronous code to asynchronous code. Synchronous code. Output. We can see that each cycle of count running to completion before the next cycle begins. Asynchronous code. Output. The asynchronous equivalent, on the other hand, looks something like this. Took 3 seconds to run as opposed to 9 seconds. The first count cycle was started, and as soon as it hit the await sleep 1, Python was free to do other work, for instance starting this account and subsequently the third count cycles. This is why we have all the ones, then all tubes, then all 3. In the output, programming concurrently can be a very valuable tool. Multiprocessing has the operating do all of the multitasking work, and in Python it's the only option for multi-core concurrency, that is having your program executed on multiple cores of CPU. If use threads, then the operating system is still doing all of the multitasking work, and in Python the global interpreter lock prevents multi-core concurrency in asynchronous programming. There is no operating system intervention, there's one process, there's one thread, so what's going on? Well, tasks can release the CPU when there are waiting periods, so that other task can use it. Output. Asynchronous frameworks need a scheduler, usually called an event loop. This event loop keeps track of all the running tasks, and when a function suspended, it returns control to the event loop, which then will find another function to start or resume, and this is called cooperative multitasking. Async.io provides a framework, an asynchronous framework that's centered on this event loop, and it efficiently handles input/output events. An application interacts with the event loop explicitly. It registers code to be run, and then it lets the event loop, the scheduler, make the necessary calls into application code when the resources are available. So, if a network server opens sockets and then registers them to be told when input events occur on them, the event loop will alert the server code when there's a new incoming connection or when there's data to be read. If there's no more data to be read from a socket, then the server then yields control back to the event loop. The mechanism from yielding control back to the event loop depends on coroutines. Coroutines are a language construct designed for concurrent operation. The coroutine can pause execution using the await keyword with another coroutine, and while it's paused, the coroutine state is maintained, allowing it to resume where it left off. One coroutine can start another and then wait for the results, and this makes it easier to decompose a task into reusable parts. Output. This example asks two phases that must be executed in order but that can run concurrently with other operations. The await keyword is used instead of adding the new coroutines to the loop because control flow is already inside of a coroutine being managed by the loop. It isn't necessary to tell the loop to manage the new coroutines.